Swayam Prabha. Digital India. Educated India.
Welcome back. We were looking at the linear instability analysis of a plane liquid sheet. This is essentially, if you imagine a liquid sheet that is flat, but has a finite thickness which is about, we called it 2h, exiting into an otherwise quiescent atmosphere. So, we look at the density of the liquid sheet was rho 1 and it was moving with a velocity u 1. The density of the air outside, if you want to call it, the fluid outside was rho 2 on the top, rho 3 on the bottom and u 2 and u 3, but essentially rho 2 and rho 3 will set equal to each other. So, it is exactly the case of a plane liquid sheet exiting into atmosphere. And one point we have to understand in all these linear instability analysis is that we are looking at the stability of an infinite liquid sheet. So, there is no such thing as a nozzle from which the liquid sheet is exiting. Now, you can do an instability analysis of what is called a semi infinite liquid sheet, where you show the presence of a nozzle and then say there cannot, you cannot have the possibility of disturbances upstream of that, and you can only have the possibility of disturbances downstream of the nozzle. Okay, but we are not going to focus our attention, we are only going to focus our attention today on the linear instability analysis of a plane liquid sheet exiting that of an infinite plane liquid sheet. Okay. So, let us look at the schematic that we have. Like I said, the sheet is of thickness 2h, the density of the fluid is rho 1 and it is moving with a velocity u 1. Uniform in the entire sheet, and rho 3 we are going to set equal to rho 2. So, we went through the process of writing the Euler's equations for both the fluids and then going through the perturbation process for the two fluids, and we came as far as calculating the pressure field in the fluid above and the fluid below. The pressure field in the fluid above P 2 is given by this expression C 1 2 e power minus k y e power I k x times e power omega t. I can write it slightly more compactly in the form that we are otherwise used to. Which is likewise P 3 and then. So, this is essentially the fluid above and the fluid below P 2 and P 3. As far as the liquid sheet itself is concerned, we went through the process of eliminating one of the variables and using the normal mode assumption we got these equations 9, 10 and 11. Okay. I can multiply equation 9 by I k and take 1 over omega d dy of equation 10 You will see why I am doing this. It is essentially to get to the form that is in equation 11. So, if I divide this by omega I k u 1 multiply by and multiply by I k. So, let me do that. Equation 9 first becomes u 1 double prime equals minus 1 over rho 1 plus omega I k u 1 p 1 double prime. So, I k u 1 double prime, you have I k times I k, that is minus k squared, but with the other negative sign this becomes k squared over rho 1 I will call this equation 12. Now, equation 10 is omega v 1 prime if I take derivative of this with respect to y, I will call this equation 13. Now, using 11, you will find that this right hand side is 0 because of equation 11. What we have, I will write this in a slightly different way, but still recognizable. So, essentially I have now an equation for p 1 double prime. This is of the form equation 14 where lambda squared equals k squared omega over omega plus I k u 1. The rho 1 cancels out. The solution to this we will call this 2 1 and 2 3 just for consistency of nomenclature. Okay. So, I have this C 2 1 and C 2 3 are as yet undetermined, and likewise you have these two constants in the pressures C 1 2 and C 1 3. So, I have C 1 2, C 1 3, C 2 1 and C 2 3. So, now I am going to go back to the schematic that we had, the plane liquid sheet. I will just copy this whole thing. This is my unperturbed configuration. If I look at the perturbations on this, so I can have two kinds of perturbations on this, and this is the fundamental difference between a plane liquid sheet and all of the analysis we had before. This problem has two interfaces as opposed to one that has always been the case, right. So, what do we do with the two interfaces? I will call the above the interface on top as eta top and the one on the bottom as eta bottom. Okay, if I write the form of eta t and eta b, so essentially y equal to eta b, eta t of x comma t is the equation determining the of the top interface, and y equals eta b x comma t Now, because of the linearity in the problem, this clearly has a functional form that is similar to the functional form that already has occurred in the pressures. I will call this eta 0 t e power omega t plus I k x. This is coming from the normal mode assumption. Okay, so, now that we know the interface shape, we can write down the boundary conditions. The boundary conditions at the T interface, which is the top interface. The first one, like we have always written, is the kinematic boundary condition. I will write it from the direction of fluid 2 and from the direction of fluid 1. From the direction of fluid 2, what I know is that V 2 prime, which is the y direction velocity in fluid 2, has to equal the partial derivative of eta t with respect to t. This evaluated at y equal to h has to equal this. From the fluid 1's point of view, V 1 prime at y equal to h has to equal the partial derivative of eta t with respect to t plus u 1 partial derivative of eta t with respect to x, and all these derivatives evaluated at the unperturbed free surface. Okay, we have discussed this at least twice during the course of the previous lectures, but I will reiterate one more point of view, so to say, that V 1 prime and V 2 prime in this equation are the Eulerian velocities at the interface, whereas the right hand side of each of these two equations is the same velocity at the same point written from a Lagrangian point of view. So, if I was a material particle on the interface and I am governed by the equation eta t of x comma t, which means the rate of motion that I am subjected to is fixed. Therefore, the material velocity at the interface, say either in fluid 1 or fluid 2, has to equal the corresponding velocity coming from the Eulerian description. Okay, that is the physical essence of the kinematic boundary condition. Now, if I write down the dynamic boundary conditions, I will call these I have two kinematic boundary conditions at the top interface. How many dynamic boundary conditions do I expect to have? There is only going to be one, because what the dynamic boundary condition amounts to is essentially a force balance on a tiny element. So, if I take an element of fluid just like that and write down the force balance on that element of fluid, that element of fluid is chosen to span both fluids, but of an infinitesimal thickness. So, its own mass is nearly 0, which means the pressures acting on both sides and the net resultant forces should all balance out. If I say force equals mass times acceleration, if the mass of the element itself is small, then you are essentially looking at something that is where the forces are all equal, it is in static equilibrium. That is what we call the dynamic boundary condition. So, with that, if I write down the pressure in fluid 2 minus the pressure in fluid 1 equals sigma times kappa. We have already gone through this process of identifying what kappa would be. If I know y minus eta t of x comma t equal to 0 is the equation of the surface, kappa is given by this minus d square y dx squared divided by 1 plus dy dx the squared raised to the power 3 half. So, if I simplify that, knowing what the form of eta is, so this is eta 0 t e power omega t plus I k x okay. This if I take derivative twice, one derivative gives me I k times this, another derivative gives me I k times I k, which is minus k squared. So, this becomes plus k squared eta 0 t dy dx is essentially I k using the Taylor series expansion that we had. I can clearly see that the minus 3 halves, this term here is order epsilon squared. So, this simply becomes so, this is the formula for the curvature. If I substitute that in the dynamic boundary condition, I have P 2 minus P 1 evaluated at y equal to h. is equal to sigma times k squared eta 0 t e power we will actually do this just to sort of show what it looks like. P 2 is known, really speaking these are the prime quantities P 2 prime and P 1 prime, because the mean pressure condition was where everything was at the same pressure. So, I can go get the forms for P 2 and P 1. P 2 is given by this C 1 2 e power minus k y times e power omega t plus I k x. So, this is C 1 2 e power minus k h times e power omega t plus I k x. This is P 2 prime at y equal to h. P 1 prime at y equal to h has these two C 2 1 and C 2 3, but this is P 1 double prime. So, we just have to multiply this by e power omega t plus I k x. So, this is simply the left hand side of this equation. The right hand side says sigma k squared eta 0 t e power omega t plus I k x. So, from here I have one equation that C 2 1 e power minus k h minus C 2 1 sin k h, sorry C 1 2 minus C 2 3 cosine k h equals sigma k squared eta 0 t. Likewise, so I have this is my equation 17, which is I have 15, 16 and 17 as the 3 boundary conditions at the T interface. Likewise, if I write the boundary conditions at the bottom interface, I will have the following. First of all, V 3 prime at y equal to minus h is equal to d eta b dt and V 2 prime at y